So let's get going. Can everybody hear me? Yeah. Okay, let's change to this view. Cool. How's everybody doing? Pretty good. Excited to be back. First day after break. Cool. So it's nice to see everybody. We've got a couple of people maybe that'll be joining us here in a few minutes, but we'll go ahead and start getting into things. So, yeah, it's been sort of a fun day back at it. One of the things that I worked on over the last few days is getting some technical stuff for the classes kind of set up to make our class meetings a little bit like up the production quality. So this is actually my phone that's recording video. I don't know if it's coming through to you all in 1080p, but that's the goal. I've got a few different things that I'll show off here. But first thing I want to talk about is some changes that we're going to make to our class meetings. And so the first is I want to, at least once a week, try to do a live class meeting where I can be here and kind of see everybody, and for us to sort of, make use of that space. I know today's class it's a 65-minute period. That doesn't mean we're not going to be here 65 minutes. We'll be out of here in probably about 30 minutes or so. So, but I think it'll be fun just to sort of be here and kind of be able to see everybody and do that sort of thing. If we're not doing a live class meeting, we're to keep the same sort of structure that we had before break with the videos and notes and sort of all that stuff. There'll be an assignment posted on my CSUS for you to access sort of all of those resources that'll be there. So we're going to kind of keep that consistent because I think that worked pretty well for what we had. Okay. Everybody's here, which is great. So that means that you found the Zoom links that are on the bulletin board. So you might have noticed a bunch of emails from Mr. Antiput. It's about some security issues with Zoom. And so I had to create a Zoom link for each class. That link will stay up there, even though the scheduled time was like for today, like at 11 a.m. to 12 p.m. That's just what Zoom defaulted to. That'll be the link that we always use. And I have the waiting room enabled. So you click on the link, you're put in the waiting room, and then I sit here and I admit folks as they show up. That way I sort of control who comes in and who doesn't. There's a separate one for office hours as well. So just keep that in mind. If you're coming for an office hours meeting, we'll be using the office hours one. If it's confusing and you can't figure out which one to use, just email me and I'll send you the appropriate link. But those will stay up there for you to access. You're probably doing something similar for other classes too. In terms of like resources and stuff that I'm giving you all, notes, videos, all that sort of stuff. The topics page on my CSUS, we got a thermochemistry topic up before break. I just added a kinetics topic this morning, and I'll start adding stuff in there as we get to it. So you'll have access to the Google folder. In fact, I put the Google folder link on that topics page as well, so you can get in there and get all the resources, and I'll list the links below that too. So you'll have access to all that stuff. So I'm going to try to organize that in a way. Again, if there's something that you wanted to, that you need, that you want to get to, but you can't find it, just email me and I'll send you the link, or I'll point you in the right direction. But I'll try to keep that sort of as easy to navigate as I can. Okay. All right. Second, gradebook changes, gradebook updates. So the big change that we made was we combined the quiz and test categories of the gradebook, and they're both under quizzes now. So before, at the beginning of the semester, you had a quiz category that was worth 30%. You had a test category that was worth 30%. Now you just have a quiz category that's worth 60%. So we just combine those two. That is only good for second semester. We didn't touch anything for first semester, but that applies to everything second semester. including the quiz that you did before break on thermochemistry, and including the stoichiometry test that you did like back whenever that was, earlier this semester. Okay, so that should like maybe ease some concerns that you have about like how we're handling assessments and all that sort of stuff. In terms of the assessments that we're doing for the rest of this semester, I would plan on like 3 or 4 more. We'll try to do one for each topic. The one that's coming up later this week is going to be a lot shorter. It'll be like an in-class quiz length type of thing. But I mean, I would plan on those. The structure of those is going to be pretty similar to like the one that you had before break, meaning, you know, it'll be open note. You can use resources, sort of all that sort of stuff. And you'll have time in class to work on that. So yeah, so that's the assessment sort of part of things. Okay. If you're looking at the gradebook and something still doesn't seem right, please let me know. I'll be happy to sort of go through it and make sure that all the changes went through appropriately. I'll have those quizzes, the thermochemistry quizzes, to give back to you before I see you in class tomorrow. I'm going to wrap those up this evening, and I'll send those your way. Okay? All right. Second sort of gradebook change, not necessarily a change to the gradebook, the second change for the semester. You all probably know we're not doing final exams this semester. Instead, what we're going to do is we're going to design some sort of cumulative project for you to work on that last week of classes. We don't quite know what that's going to look like yet. It'll be something where you get some sort of choice and agency and like what you want to focus on, some creativity and sort of like how you want to structure it. If it's a video, if it's a presentation, if it's something else, it'll be project based. We might let you all sort of collaborate on that. I'm going to say that likely you'll be able to collaborate on that. So we'll get all that stuff. We'll get those details to you in a few weeks, but do expect some sort of like cumulative thing for the end of the year. But it won't be like a test or a quiz. It'll be something a little bit more sort of project based. And we're still sort of working that out, but I wanted to give you a heads up on that as well. Okay. All right. Does all of that sound okay? Are there any questions about those things? Okay, cool. So let's jump into our topic for today, which is chemical kinetics. I put the link to those notes in our Zoom chat. They're also up on the resources if you want to get them and follow along. I'm going to go through pretty much the same stuff that I went through when I typed up the notes, but you can write this down or sort of add to what you've got there. Yeah, let's see how this goes. So we're going to jump over to the whiteboard like that. Nice. Okay, so chemical kinetics. And let's adjust this a little bit. Nice. Okay, so the one thing that I want to say about kinetics is this is a really, really big topic, and there's a lot to sort of talk about here, a lot that we could talk about. For our purposes, though, it just works if we go in and we sort of just do like a conceptual like overview of it, which is what we're going to do. So we're going to talk about what we mean by the rate of a reaction. We're going to talk a little bit about collision theory. And then we're going to talk about, most importantly, factors that affect the rate of a reaction, right? What could we change to make a reaction go faster or make a reaction go slower? There's a whole quantitative side to this, right, where we can measure reaction rates, we can change reaction rates, we can control it and do all that sort of thing. We're not going to get into that. We wouldn't even get into that even if we weren't sitting here on the computer working with each other, right? So understand that like this is a really kind of rich topic, right? If we're working in industry and we want to optimize how long it takes to like make a product, right? We have to understand the rate of that reaction and how we can control that, right? What can we do to speed it up? If you're like working in pharmaceutical industries, if you've ever taken a medication that was like a time released capsule, or something like that, that's chemical kinetics, right? We have to slow down that reaction so that it releases over the span of like, several hours versus like just a few minutes or whatever it may be, right? So kinetics, right, really plays a role in a lot of different things that we encounter day to day. And again, here we're just going for sort of conceptual big picture here. So I guess the first thing that we should say is, like, what do we mean when we say, chemical kinetics? Well, we're talking about how fast or how slow a reaction is. Right, and we've seen a lot of reactions this year that are like really fast, right? They're just instantaneous, they happen. Some reactions naturally happen a lot more slowly than that. Maybe they take minutes or even more than that. They may take hours to happen. It just depends, right? It depends on the reaction, depends on the conditions. And we're going to talk a little bit about those conditions here in just a few minutes. When we talk about how fast or slow a reaction is, right? What we're talking about is called the rate of the reaction, right? So how quickly this reaction is proceeding. And we can quantify rate of reaction. So let's look at an example real quick. And we'll use this example because I know we've talked about this reaction a lot this semester. So 1N2, 3H2, 2NH3. So when we're talking about how fast this reaction's happening, we can define that rate in a couple of ways. One way that we can define and measure it is we could say, well, N2 and H2 are the reactants here, right? And they're being consumed, right, over the course of this reaction. So we could talk about or measure the rate of the reaction as the disappearance or consumption of reactants, right? So how quickly those reactants are being consumed. We could, measure the concentration of N2 and then, a few seconds later, measure the next concentration of N2 and then get an idea of how quickly that N2 is being used up. We could also measure it in terms of how quickly those products are being produced, right? So NH3 initially is at a concentration of 0. There's no NH3 present. But if, a few seconds later, now there's NH3 showing up. And so we can take that difference, right, and say, okay, well, here's how quickly NH3 is being produced in this reaction. So you can define the reaction rate either way, right? And more specifically, you can define the rate of the reaction with respect to anything that's in the chemical reaction. And so let me give you an example. So let's say we're looking at nitrogen in this case, and I'm just going to make up a number. But nitrogen is disappearing, right? Because it's a reactant, so that means it's being consumed. But it's disappearing at a rate of 0.1 mole per second. So each second that goes by, 0.1 mole of N2 is being used up, right? That's the rate with respect to nitrogen. Now we could also define this rate with respect to H2, right? Same rate. If nitrogen is disappearing at 0.1 moles per second, H2 will be disappearing at 0.3 moles per second. And what I want to point out here is that the mole ratio between H2 and N2 is 3 to 1, and the rate with respect to H2 to N2 is also 3 to 1, right? If hydrogen in this reaction is being consumed 3 times as quickly as nitrogen, then the rate is going to reflect that. So these two things here are in a stoichiometric ratio, right? Meaning the mole ratio still applies. And so it's important to understand how we're defining the rate, right? Are we defining it with respect to N2? Are we defining it with respect to H2? Because it looks really different, right? 0.3 looks quite different than 0.1, even though they're representing the same rate for that reaction. It just depends on what we're measuring and what we're looking at, right? Likewise, we could measure the production of NH3. So if nitrogen is being consumed at a rate of 0.1 moles per second, then that means NH3 is going to be showing up at a rate of 0.2 moles per second, right? And that's appearing because, or being produced because it's a product, right? And so again, you'll notice that the ratio here in the equation, 1 to 3 to 2, is maintained with those reaction rates, 1 to 3 to 2, right? So all that stoichiometry stuff still applies. So if you're given the rate of one thing, you can find the rate with respect to another thing just by using mole ratio, essentially. Okay? So I just wanted to mention that. Hold on, I'm going to mute myself while I take a drink. Okay, so I just wanted to mention that because I want you to understand that, we're not, breaking any of those stoichiometry rules. All that stuff still applies. It just kind of looks a little bit different here. Okay. Now, in terms of quantifying rates of reaction, in terms of putting numbers on it, this is really the only stuff we're going to do with that. We are not going to really measure any reaction rates or try to derive any reaction rates or anything like that. It's beyond the scope of our plans for this year. But if you're given a reaction rate, understand, one, that the bigger the number, that means the faster that reaction's happening, right? And then also you could stoichiometrically relate two rates to different things in a chemical reaction. Okay? Is everybody all right with that? Okay. So here's our big idea as we sort of kind of look ahead to the next couple of things we're going to talk about. The rate of a reaction is not constant. What I mean by that is, and I've totally made these numbers up here for this example, but if we're saying that the rate of this reaction with respect to N2 is 0.1 mole per second, right, is the rate that N2 is disappearing, it is not always going to be 0.1 mole per second. We might see this reaction in a different context where it's 0.5 moles per second, right? Or it's 0.05 moles per second. It totally depends on conditions, totally depends on where we start, temperature, pressure, all that sort of stuff. And we're going to talk about that a little bit here in just a minute. But understand the rate of the reaction is not constant. In fact, that rate will decrease as the reaction proceeds. We'll talk about that a little bit more here in a couple of minutes. Okay, but don't get bound to the idea that these rates are defined for a specific reaction because they're not. They depend on conditions. They depend on a number of factors. Yeah, Reza. Yes, definitely. And we'll get into that here in a little bit more in just a minute. Yeah, absolutely. Okay, so that's putting numbers on reaction rate. Okay, those are the only numbers we're going to look at today. The rest of this is going to be conceptual. So let's move down here a little bit. So before we jump to factors that affect the rate of the reaction, I want to talk a little bit about how these reactions are happening. And I know we've mentioned this before, but we'll just do a quick review on this. We'll talk about collision theory. So we know that when two things react with one another, it's the valence electrons that are interacting, right? So what we need is the valence electrons of this reactant to be able to interact with the valence electrons of this reactant. And the way they do that is they have to be able to touch. More specifically, those particles have to collide. And that's what collision theory essentially states, is that a reaction occurs when the reacting particles, that's the reactants, right? Experience we're going to call it an effective collision. So an effective collision, and that's really key here, right? There are particles all around us right now that are colliding with one another, but they're not reacting. So what do we mean by effective collision? Well, just because two things bump into one another doesn't necessarily mean a reaction is going to happen. There have to be a couple of other things that are also true. And the first thing that when we talk about an effective collision is that when they bump into one another, they have to have sufficient energy to overcome the activation energy of the reaction. Right? So there's a minimum amount of energy that's needed in order for the reaction to begin. So just because two things sort of bump shoulders with one another doesn't mean that they're achieving that minimum amount of energy. They have to collide with enough energy, with enough force to get us over that initial bump, right? We call that the activation energy barrier. So they have to have sufficient energy to do that. And so that's the first thing. So again, a lot of things are bumping into each other. That doesn't mean a reaction's happening, because the reaction for those two particles has an activation energy that's higher than what that bump can overcome. The other factor, one that we won't talk about too much for our purposes, but I do want to mention it because it is kind of important, is that in some cases they have to collide at the correct orientation. And this is really important when you've got like a big molecule, right? So you can imagine like a really big molecule that's got like a polar end up here, right? It needs to collide with another big molecule, and you've got to get the two polar parts to collide with one another. So just because those two big molecules bump into one another doesn't mean that the two parts that need to react are actually going to find each other, right, in that collision. So you have to get a correct orientation, right? And it might be that, one's flipped around or whatever, right? Sometimes that's important. Again, for our purposes, we don't really get into that because we just assume that, these reactions are like fairly simple, just sort of like basic spherical particles. But sometimes that's a really important factor to consider, right? So that's collision theory. So these particles bump into each other, we get an effective collision, and that effective collision produces a reaction, right? And we're going to talk about some of the factors that determine whether or not a collision is going to be effective or not. Or determines how many effective collisions happen. Okay, so the big idea here is that if you can increase the number of effective collisions, you can increase the rate of the reaction. Okay, so increasing the number of effective collisions increases the rate of the reaction. So we're going to go through, we're going to look at 4 factors that affect the rate of the reaction. And for each one of those, we should think, okay, if this makes more effective collisions, right, then that's going to increase the rate. And so that's sort of how we're going to approach all this stuff. Okay, let me move the whiteboard up a little bit. There we go. Okay, and there's much more to collision theory than that. I just wanted to give you sort of like a just sort of a general overview for that idea, because we're not gonna lean too heavily on that theory. But okay, so factors that affect the rate of a reaction. And I've got four for us to consider. Depending on the source you look at, you might see these broken down into 5 or 6 different things, but they all sort of speak to the same thing. Okay, so factors that affect the rate of the reaction in no particular order. The first one is temperature. And this is the big one, right? And a lot of folks like make this association, right? If we have a reaction and we increase the temperature, right? If we heat that reaction up, the reaction is going to go quicker, right? It's going to speed up. So we know that temperature is directly connected to kinetic energy, right? We talked about that when we talked about gas theory and stuff. And so that same idea still applies here, right? Where if you increase the temperature, you're increasing the kinetic energy. And so what that means is that if those particles have more kinetic energy, the collisions now have more force, and so they can approach that activation energy barrier. So they're colliding with sufficient energy to overcome that minimum energy that's needed in order for the reaction to happen, right? So the effect that we see is increasing the temperature increases the rate. Right? And the opposite of that is also true, right? If we cool a reaction down or if we decrease the temperature, we're going to see that reaction slow down as well for the same reason, right? You're reducing the kinetic energy of those particles. So now they're not colliding with enough energy to overcome activation energy barrier, right? That's a pretty easy association. Okay. Second thing, as Reza mentioned just a couple minutes ago, is the concentration of the reactants. So at a given temperature, right, even if we don't change temperature, at a given temperature, if you have a higher concentration of reactants, that means if there's more stuff there to react, you're going to get a faster reaction. And the reason for that is statistically, that means that you're going to get more effective collisions because there are more collisions happening. And so more collisions happening means a higher likelihood that you'll get an effective collision with enough energy to overcome the activation energy barrier, and you'll see a faster reaction. So higher concentration means a faster reaction, faster rate of reaction. And there's also another aspect to this. So let's go up here and let's look at our reaction that we were talking about. So that means that in this reaction, into an H2, right, our initial concentrations, whatever they are, these two things are being consumed in the reaction, right? So that initial concentration is decreasing. So the rate of this reaction actually will decrease over time because you're consuming the reactants. And so you're going to have less stuff there to react as the reaction proceeds. And so your reaction is going to appear to slow down, and it'll appear to stop. It actually doesn't stop. We'll talk about that. That's our next topic, is equilibrium. But it actually the reaction appears to stop, right? So that rate goes to 0. So again, the idea that the rate of a reaction is not constant is really important. So not only is it temperature dependent, or it's dependent on a couple of the other factors that we're going to talk about here in just a second, it also will change throughout the course of a reaction, right? So often we talk about, like initial rates of reaction, or the rate at, this specific time, because that rate does change over the course of a reaction. Okay, let's hop back down. Let's talk about our 2 other factors. Number 3, and so I've phrased this one specifically because you're going to see a couple of questions coming up on assignments or on assessments that sort of speak to this idea. So that's the reason I phrased this in this particular way. But the surface area of the reactants also affects the rate of the reaction. And so let's think about it this way. If we have a beaker of HCl, right, beaker of hydrochloric acid, and a big chunk of metal that we want to put in that beaker. So let's say it's zinc, right, a big kind of like just rock of zinc metal. When we put that zinc in that HCl, those reactions are going to happen only where the HCl can contact the zinc. So all of the zinc atoms that are down inside that big chunk of metal aren't able to react because they're not exposed to the HCl, right? They're just surrounded by other zinc atoms. If we take that same piece of zinc, right, same mass of zinc, same amount of zinc, and we crush it up, we either granulate it or we make it a powder, right? Now there are many, many more zinc atoms that are able to encounter the HCl, and we're going to see a faster rate of reaction. So surface area is one that's often overlooked, and there are several sort of historical kind of, I guess you call them disasters, where the surface area of reactants has led to like explosions because that reaction happens so quickly in an unanticipated way. And you'll see a couple instances of that coming up later this week. But the idea here is the greater surface area faster the rate, because you're able to get more collisions because there's more stuff to collide. Okay. And then the last one that I want to mention, which is sort of, if I asked you the question, well, how could you speed up a reaction, is probably the first thing that comes to mind, and that's a catalyst. And that's not how you spell catalyst. That's the wrong pen. There we go. So a catalyst lowers the activation energy of a reaction. And so what that means is, now that activation energy barrier is lower, the particles don't need to collide with as much energy in order to overcome the activation energy, and so you get a faster reaction, right? Because essentially lowering that activation energy barrier means that collisions are more likely to be viable, right? And so you get a faster reaction. So catalysts don't actually shorten the distance between like the start of the reaction and the end of the reaction, right? They just lower that activation energy barrier. You know that catalysts aren't consumed in reactions, so we don't need to be worried about like stoichiometrically what ratio they're in. A very small amount of catalyst can have a profound effect, because a catalyst will catalyze this reaction, and then it's able to go catalyze another reaction, and then another reaction, another reaction, another reaction, right? So they don't necessarily occur in stoichiometric amounts. Specific catalysts, right, depending on like the reaction and depending on like what catalyst is needed, operate in different ways. So it just sort of depends on the catalyst, depends on the mechanism. We do not need to be concerned with how does a catalyst lower activation energy. That's a much sort of bigger topic that's beyond what we need to talk about here. It's only the idea that the activation energy is lower, and if the activation energy is lower, then the reaction is going to proceed more quickly as a result. Okay? Yeah, Reza. Yeah, so like I said, depending on what source you look at, there might be some other sort of phrasing to these factors. So like a fifth one that gets thrown out a lot, like in one of the textbooks that I pull stuff from, is the ability of the reactants to come into contact with one another. So that might be phase, that might be like what you're talking about. Yeah, so stirring, like that sort of thing. So just making sure that those reactants can actually have effective collisions. Yeah, so definitely, things like that are things to consider. All right. Okay, any other questions on those ideas? Okay. So again, really what you need to be concerned with here is, if I say, okay, here's a reaction, here's its rate at 20 degrees Celsius. If we run the reaction at 30 degrees Celsius, what do we expect the rate to be, right? We expect the rate to be greater. It's going to go faster because more kinetic energy, more force when they collide, more effective collision, right? Okay. Let's talk quickly about homework and other stuff for this week. So I did pull sort of just 4 conceptual questions for you to look at. I might add a 5th one there for you to consider after I let you go here in a couple of minutes. But that's up on my CSUS Kinetics homework. I'll have the answers posted this evening as well, so you can sort of check what you're doing. If you want to read the Kinetics section of the textbook, it's section 18.1. So you can go check that out as well to give you a little bit more information. Okay, Kinetics notes are also up on the topics page. You can look at that too. It's sort of the same stuff that we've talked about, but that might be helpful. Okay, so that's for tomorrow. Now, tomorrow's class is planned to be asynchronous, meaning I'll give you the resources on my CSUS and you all will be good to work. I will be here if you have questions, but you don't need to come and like hang out with me unless you want to. You can come hang out. But I'll be here if you have questions, but all that stuff will be up. Right now, I'm planning on an in-class Kinetics quiz on Friday for you all. That'll be real short, just a couple of questions. And again, we'll take time on Friday in class to do that. That might change. It won't be any sooner. Like you won't get it tomorrow. I might push it to next week. We'll just sort of see kind of how tomorrow goes. Okay. The last thing, and maybe most importantly, is let me know like what you all need, right? I'm anticipating some challenges. We're making some changes. Dr. Herricker and I have kind of talked about things, what we can do. I'm here to be flexible. I'm here to sort of help. I know it's like it's a weird time. It's a bummer that, we're not going to be in the same room, working on stuff again this year. So if there's anything I can do to help in terms of resources for class or, structuring something a certain way or whatever, know that I'm all ears. I'm here to sort of hear those suggestions, hear that feedback. But yeah, otherwise, that's all I got for y'all. So you're good to go. It's great to see everybody. Everybody's looking good. Welcome back. Yeah, we'll see y'all tomorrow. Bye. Bye.